Well, welcome to the 7th workshop dedicated to motion control applications in large facilities. It is a Zoom meeting, and we've done it as a Zoom meeting rather than as a webinar, so you can all turn your microphones off and on. It would be grateful if you could turn your microphones off during a presentation, and that way we can just concentrate on the speaker. But after the presentation, then there'll be Q&As where you can feel free to join in. I'm sure any one of the organisers will mute people if it's getting a bit of a free-for-all, and we might then refer to, please put your hands up. But we'll see how we get on. Okay, so welcome once again. Now this worked on all 5 dry runs. So why do we do motion control MOCRAF workshop? Who does the MOCRAF workshop? What do we do at the MOCRAF workshop? And this year, being awkward and strange as a Zoom, how are we going to do the MOCRAF workshop? So why? As we said, motion control is a key element which enables a high level of performance at scientific facilities. More and more in the need to automation and speed up experiments, or experiments are in places where we can't approach, then the need for motion control is ever present. And as the precision of the experiments becomes more and more demanding, then motion control becomes a discipline that requires ever more application. There have been 6 previous workshops. The last 4 of them have been part of the ICALEPCS program, as indeed is this one. So this is an ideal, if an unusual, way of meeting friends at this workshop. So what do we discuss? We discuss our experiences in motion control, technical solutions, software, hardware, maybe kinematic transformations, complex trajectories, protection and collision avoidance, multi-axis and multi-controller synchronization, embedded or hosted motion features, closed loop systems with different feedback sources, and maybe some vibration control. In robotics, we'll look at some industrial robot arms, collaborative robots, implementations, experience of robots using X-rays, integration into control system, tangos and epics, and maintenance. And then experiences in metrology. As motion control, we drive ever closer to the nanometer, and in some instances below. Then how do we evaluate the stages that we use in our motion control applications? How do we characterize them? How do we model them? How do we make them better? And what tools do we use for modeling and improving motion control? And what are our experiences at getting down towards these sub-micron, sub-nanometer positioning? What are our experiences in continuous and synchronous motion control and synchronizing movement and detector acquisition? These are the topics that have been covered and may well be covered some more today. So, who? Well, there's a link to a Google map that will show you where all of the participants are of our previous workshop, where all our industrial collaborators have come from, and highlights the new attendees for this year. So this year we had 66 attendees booked from 14 countries and 26 different institutes, and we have 3 industrial partners or trading companies with us today. So what are we going to do today? So in the workshop sessions, they'll feature 2 longer talks, presentation on a topic of interest to the particular workshop, 15 to 20 minutes, with then a discussion of 5 to 10 minutes. And then there'll be a roundtable discussion where we will split out into breakout rooms. And before we do each of those, we'll share a slide as to which breakout room we would like you to join. And the topic questions for that individual breakout session. For the speakers giving the talks, and this year, because it's a bit short, please 15 minutes if we can, and that'll give plenty of time for discussion afterwards, if we please respect the speaking time. We won't have the ability to waft a clock in front of your face this year with a flashing red light telling you you're in your final seconds. Okay, so this is the introduction in the first 10 minutes of the presentation. In the first session then, our colleague Xavier will discuss motor types and what is the state of the art and how they're evaluating different types of motors at Alba. And then followed by an overview of the mechatronic applications at Sirius beamlines. Is Renan still the presenter? And then after, we'll have a half-hour breakout session. In the half-hour breakout session, 15 minutes amongst ourselves, and then a couple of minutes afterwards for each breakout room to present key findings. So 15 minutes of discussion, followed by a summary of what each workshop did. Then after the break, we'll discuss robotics for pick and place applications at Soleil, and robotic RAHDD, robotic arm holding diffraction detector. We like our acronyms, don't we? So I shall talk about how we integrated a robot arm, a commercial robot arm for detector positioning. And then we'll have a second breakout to discuss our shared experiences in integrating robotics. Then we'll have a talk from Beckhoff on magnetic levitation technology, and a talk on collision avoidance from Soleil. And then it says I'll be holding a conclusion for half an hour, but that usually might involve another round table. Have we got 3 round table, Eve Marie? No, just a 2. Okay.
Yeah,
all right. Just a 2. Well, there we go. Okay, so welcome everybody to this workshop. If we all take part, we'll all get the most from it. So without further ado, we'll hand over to Xavier to get ready and present his talk.
Let me share my screen. And I start the presentation. Can you see the presentation?
Yes, thank you.
Okay, perfect. Well, the aim of this presentation is explain a little bit the state of art of the motors and the different alternatives that we have used in Alba and why we are using these ones. Main of the presentation will be centered on different types of motors, but then I will explain a case that we are in design, and we are in construction, measuring and doing the metrology of the device, and that's the idea, to mix everything a little bit. Okay. So first, here is the device. Right now, here is the 3D. So big part of the design is already done. But in the beginning, we have some requirements that we have to achieve, and some of them are not easy to achieve. The first is it's a goniometer. So we need a very good precision with a resolution of 20 microdegrees and height speed at 1 revolution per second. And one of the things that are also important is the speed stability, and also the runout and the wobbling of the top of the goniometer. And to achieve this precision on the top of the goniometer, the first thing is to construct a good goniometer, but also try to correct, if it's necessary, with stages that are rotating on the goniometer. So these stages here, the X, Z, and Z, in principle, it's to position the sample, but also depending on the features that we can achieve with the goniometer mechanics, we have to correct to achieve the confusion sphere under the 100 nanometers. When this project arrives, we have to start to think in which motors we want to use, because some of the motors, the standard motors that we are using in Alba, it's steppers, and it's not possible to achieve all the targets that we have with this kind of motors. So we studied not only for this project, also for this for other projects, which are what we are looking in a motion system. So the first thing is we have a design that comes from the scientists and also from mechanical engineers, and we have to fit the motors with these requirements that comes from these two people, or these two groups. For us, it's also important, and more nowadays than in the past, that to have the possibility to synchronize motors between them, because flying scans or continuous scans are most often, and it's a necessity nowadays in synchrotron. Also, it's important to simplify the integration with the control system and do a simple design, because we will construct just one. So the time invested in the development and in the assembly is more expensive than the pieces itself in most of the cases. So the idea is to keep it simple in design and in the integration of in system controls. Another important point for us is the possibility to standardize the motors to minimize the spares, and if we have some problem in some motor, to have a easy change of this motor, or also in the control system, in the control electronics, to have a spare one, it's always good. Also, it's important the low working on maintenance, and maybe not in all applications, but good position accuracy and detent torque, it's good features, and always have applications that you need special features, like motor in vacuum, or in a magnetic environment, or low or high temperatures that have to be in consideration. When we look at the family of electric motors, there are a lot, and some of them we can discard because do not fit in our needs in a synchrotron light source. One is DC motors that uses brushes. For us, it's not good because brushes means that you have electric noise for the sparks that are generated in the brushes, and also for the maintenance of this kind of motors. Another kind of motors that we try to avoid is asynchronous motors, because in general, the features that you can achieve with a synchronous motor are better than the ones that you can achieve with synchronous motors. And price, that is one of the good things that have this kind of motors. It's not a big issue in when you are doing just a prototype. So let's check a little bit the technology of the motors. First, we start with 3 types of steppers that we have. The first one, it's a permanent magnet stepper motors. This is the simple motor that you can imagine when you try how a motor works. This is, we have a magnet, a permanent magnet as a rotor. And then on the stator, you have different coils. And when you are generating a magnetic field in this direction, the magnet is aligned with this direction. And when you put in the magnetic field in the other direction, the magnet and so the rotator change the direction with the magnetic field. This is, well, we will check then with the different steppers. So this is another type of a stepper. This is a reluctance, variable reluctance stepper motor. This is the rotor, it's a ferromagnetic material, and what you do is generate a magnetic field and minimizes the flux. Well, the ferromagnetic aligns with the magnetic field with the aim that like a compass that tries to align with the magnetic field the needle. So here we don't have a magnet, so we need more than two phases. Like if you see this motor, if we change the magnetic field to the other one, the motor can rotate in one way or in the other way. So we need at least 3 or more phases to ensure that the rotation goes to the good direction. But respect the other motor, here we can make a lot of this kind of a configuration, and we can achieve a lot of steps during the rotation. Only with 2 phases we can achieve a lot of steps for doing a revolution, so we achieve more resolution. Here is a combination, it's the hybrid synchronous, and takes the best of the 2 motors. We have here an axial magnet with 2 rotors with ferromagnetic material. And here we have most of the advantages of the 2 motors in one. Here we have a comparison of the 3 stepper motors. We in Alba use always hybrid motors, and they are the ones that are easier to find in the market. So the features are much better. The torque is higher. The resolution, the step angle are small than the other ones. You have detent torque that is very important in our applications, and that's the thing. Another kind of motors are the AC motors. The synchronous motors are uses a permanent magnet, or generally there are different kind of constructions, but most of them uses a permanent magnet inside. And the main thing is that when you change the frequency of voltage in the coils, is the same frequency that you will achieve in the rotator with the permanent magnet that is following this magnetic field. Another kind of motors is the synchronous that I told before that we are not using, because one of the things that we lose is that this is synchronous, because we don't have a permanent magnet. You have to induce use magnetic current in the rotator by the magnetic field that you generate on the stator, and then you changing this the stator orientation of the magnetic field, you generate the rotation. But this rotation is always slower than than the rotation of the control system. So you lose a little bit of the control. So we always use synchronous motors in our facility. Here we make a comparison of the two selected motors that we are using. The steppers have better position accuracy because the movement is smaller. The steps are you are moving as when you change the voltage in the phases, you are moving very few degrees. And in case of the AC motors, you have to use micro stepping and for better accuracy. You can implement a closed loop in the stepper motors, but it's not necessary because you can control, you know where is the motor, and you have most of the accuracy that you have mostly comes from the steps that you have in the stepper. But anyway, when you have high speeds, you can lose some steps, and closed loop can correct these lost steps to keep in the correct position. One other important point is that the stepper motors of this type have an important detent torque and also without power. So it's like if you apply a brake on the motor without have the brake on them. One of the problems that have these kind of motors is the speed that the torque that decreases with the speed. So at the high speeds, you don't have much torque, and motor can become stuck. For the other side, the synchronous motors, you can achieve more speed, also because at high speed you have a high torque. The closed loop is used in a different way. When we have a closed loop in synchronous motors, it is called servo motor. And the idea of this closed loop is to keep the maximum torque on the rotator. This is done by achieving that the magnetic field that you generate with the stator is always at 90 degrees of with the orientation of the magnet. And with this, you achieve much torque than with a stepper. So these are different motors, but they covers different fields. Another kind of motors, it's piezo motors. The first one is piezo actuators that you can have big pushing forces, but the problem that you have with this is that the range that you can move is very, very slow. The last years appears piezo motors that uses different technologies like a slip stick or these legs that makes these movements, that you can achieve big ranges, but biggest torques of movement. But the problem is that you reduces the force. The force that they can generate is very small, and it's difficult to control. They are using not a sinusoidal signal. They are using more complex signals. So if we can check also our requirements, and we see that depending on the application, we need one motor or the other. Here I elaborate a table that makes a summary of the things that we talk just here. Here are the 4 motors that we are using in Alba. Maybe there are some that it's not in these 4 types, but most of them are here. And here we have the main features to select the motor. And for high resolution position, we have steppers. For speed, we have AC synchronous or servos. And for compactness, we have piezo motors here. Okay. And here in our case, at the end, what we do is we choose for the rotation AC synchronous motor with 18 phases for achieving better resolution, and it's a direct drive. There's no reductions on this, and it's a aerotech motor and aerotech controller. And on the top here we have a piezo stage that it's from Smaragd, that it's controlled by a Smaragd controller, because this kind of motors uses its own controller, but the input signal is the step direction that comes from the aerotech controller. This is used by because its compactness and reduces an uniform inertia that could generate bowling or out of the system. On the top, we are using piezo stages, 3 in parallel to achieve more forces. And also for the table, that it's a thing that you just move in the beginning of the experiment. We are using steppers like in the past. Here is the performance. You can see that we achieve in the first measurements what we are looking for. And here the acknowledgements of people that helps me and companies. And that's all. Thank you very much.
Okay, thank you very much. Any questions for Xavier? Just unmute and dive in.
I have a question, yeah. On the aerotech motors, yeah, sorry.
Yes,
on the aerotech motors, did you say what kind of motors they were? I must have missed it.
The motor, the exact model, I remember it's...
No, just general type, I guess is enough.
Here we are using AC motor with a special feature that is the stator do not have ferromagnetic material. There are no, I don't know how it's called in English. There's no core in the coils. This is the idea of this is to reduce to make the magnetic field more not so sharp, and make the speed more easy. So when you are running, you cannot see the poles during the rotation, because if you have a ferromagnetic coil of on the coils, ferromagnetic core on the coils, you see that when you are close to this coil, the force is bigger. So after talks with Aerotech and other manufacturers, we decided for this kind of motors.
Okay, thank you. And just follow-up question on, you said that your Smaragd state controller, it takes step direction inputs from the Aerotech controller, is that it?
Yes.
All right,
this
so
is because,
the Aerotech.
The Aerotech is the brain of this synchronization. In Alba, we are using ICALEPCS, but in this case, we want to use the same controller for the motor and the controller of the motor. We want to use the same company to avoid problems, and also because we need, if you see one of the features that are asked, it's 1 revolution per second with a resolution of 20 microdegrees. This if you have to enter the analog signal of the encoder directly to the controller and make the interpolation inside. In other case, it's not possible because you need a signal of 300 megahertz, and it cannot be achieved with a Hayden-Henn interpolator or a Renshaw interpolator. So for this reason, we select the relative encoders, and we make the interpolation inside the controller of Aerotech.
Last question on that. Since you were using Smaragd stages, did you see the effect of the stick slip action? That every few microns or so you see a little vibration?
Yes, we see this effect, not in this project because we have not started the metrology of Smaragd stages. Right now, we just started with the goniometer itself, the omega axis. But in other projects, we see the effect of a slip stick. Yes, it's difficult to achieve a constant velocity. But here, the idea is to correct the bowling of the system. So we hope that we have to move very few, very small range, and we think that we can correct just in a stick stage or in a stick phase. That maybe we cannot go to. It's not necessary to go to a slip phase. And only with a stick we can achieve this, and we think that we can avoid these problems.
Okay, we have a question from Maxim.
Hi, thanks for the presentation. I hope you can hear me.
Yes,
we can hear you.
Perfect. So you said you used an Aerotech controller as a master. Do you know which type do you use? Is it an ensemble or a soloist, or what type
no,
of?
This is A3200 that right now it's obsolete. And
exactly.
Yes.
Do you know for which one you want to change?
No. We want to use this one because we want to use a linear amplifier, and the new ones cannot. You don't have this possibility. The idea is that Aerotech says that they trust more in the linear amplifier for less noisy and more uniform, more smooth movement. So we decided to go for this one that is obsolete because the amplifier that fits the servo motor, the AC motor, it's a linear amplifier, not a
PWM.
commutator. Yes.
But isn't the ensemble or something like this also using linear amplifier? Because I think the DCM at the ISREF uses this one as well. But,
okay, I don't know. We are
okay. I think can I interrupt? We've had a good discussion. Thank you very much. We're ready for our next presenter now. Next presenter is from Sirius. Who's presenting?
Yeah, it's me. Hello, you hear me?
Hello, Renan. Do you want to try sharing getting your presentation and slides ready?
Yeah, let's see how it goes. Which screen do you see? Is it the Chrome
nice
browser?
Background.
Nice picture.
Okay,
you
great.
Your screensaver or wallpaper.
Okay. Right, so I think it's going to go right. You see it?
Yes, thank you very much.
Okay. All right, so welcome everyone. My name is Renan. I'm speaking on behalf of the Beamlines Engineering Division and Operations Software Group at the Brazilian Synchrotron. And I'm going to give you a review of the mechatronic applications at Sirius Beamlines. This is a work of many brains and hands, and I'm honored to be representing them here today. I also thank you for the invitation. So this is our campus. It's in Campinas, close to São Paulo in Brazil. And we have Sirius fourth generation light source, which just started working. And we had a second generation light source, UVX, which was decommissioned last year. We also have a biology lab, a microscopy lab, and a renewable sources lab in the same campus. It's a high-tech campus here in the city. This is a picture of our experimental hall in 2018. And this is an update last July. So you can see that it moved pretty quickly. We expanded to a lot of beamlines. At the moment, we have 4 beamlines which are open for users, 1 that is under commissioning, 3 or 4 under assembly, and we have a few more waiting to be for funding or planning. Going very quickly over our ecosystem in controls, we have a few legacy items from the previous source as Galil and MOCRAF. And for series, we are mostly based on Delta Tau motion controllers and Compact Rio for the high performance systems. And in terms of software, we cover a lot of packages. I think most of you are aware of all of them: Python, Linux, and so on, virtual machines, GitLab, and many collaborations with different synchrotrons and labs in the world as well. I will start with the high dynamic double crystal monochromator because it's one of our biggest projects, no doubt about it, and it tells a lot of our way of working on the recent years. So the basics of the story is that we have a source, a broad X-ray source, and then we use 2 crystals to keep a monochromatic beam with fixed exit. And the issue is that as there are displacements or errors in positioning one crystal with respect to the other, we would see a variation in the source, and we want to keep it low. That's the message. So a few years ago, we discussed that 10 nanoradians RMS up to 2.5 kilohertz, which is a broad bandwidth, would be our target. And this meant 3 times better or 5 times better than anything that was available at the market at the moment. And we also wanted to go from static performance, so just step scanning basically, to fly scan as well. So we wanted to keep good performance while moving. And this basically led us to take a route. So we are moving, what I like to say, that we are going from automation to real high-end mechatronics, where all the sensors matter, all the actuators matter, and we need to take a complete integrated view of the mechatronic system. And then we might wonder, well, how many trials and errors we have to take before we get to that step? And the answer is, well, ideally none, right? So we want to do it first time right. That's the concept. So we started in 2015, and we were fortunate enough to have very good coaching and partnership with MI partners in Holland. And we applied technology in the semiconducting industry to bring a completely different type of monochromator to life. So this is a concept in the whiteboard. It evolved to lumped masses, and then the CAD drawings, the first basic core unit, and then already go into the beamline and online validation. And we were very successful in taking that as a single continuous work. And this was based on this tool that we call dynamic error budgeting. It's well known in the semiconducting industry, and it allows us to perform high mechatronic predictions, basically. This is a lumped mass model. I don't have the time to go into too many details, but it basically shows the 2 crystals, the first crystal, the second crystal, a few sets, a goniometer, a system that positions the second crystal with respect to the first, our granite base, and so on and so forth. And what the concept says is that we have very clear specifications in the beginning. We need to know the disturbances that are acting in our closed loop system. Then we are going to come up with a conceptual design, which eventually becomes a mechanical design. And from there, we iterate with a mechatronic model, planning and modeling disturbances and designing controllers until our requirements are fulfilled. So it means that we are not building thousands of prototypes or trials and errors before we get to the performance that we like. This is the dynamic error budgeting, the DEB diagram, and here is the control loop showing where the controller acts, and then the digital to analog converters, its disturbances, amplifiers, its disturbances, the plant, which is subject to the floor, to liquid nitrogen, and then the sensors, and also the disturbances from the sensors, and all of this is coming together to give our final prediction of what's going to happen. And here I show some summary results. This is the model, and what is nice about it is that you can also check for the different sources. So it's a little bit small. I hope you can see it. We have actuators, sensors, liquid nitrogen, and floor, and we can just say, hey, this is the resonance that is giving me the most contribution to my final performance. So I have to improve what the liquid nitrogen is doing in the system. If it were the actuators, I would know that I need to improve the actuators or the sensors. So this gives us a route on which is the key element defining the performance of the system. And also it tells the story about the dynamics. So how is the plant and which are the resonances in the system, or which architecture changes we have to make it compliant. So this is only a model showing all the different disturbance sources. And here we are comparing experimental data, which is in yellow and red, with the model, which is in blue. And then we can see that we can actually predict very well. And even this large jump that is provided by the liquid nitrogen system, because you see that in the yellow, but you don't see it in the red, it's because of a known effect. So this gives us confidence in moving forward and towards the specifications. This is another plot of experimental data. It shows different running speeds for the cryogenic pump and also different designs for the manifold. And we can see that as the manifold goes bad, the performance also goes bad. And this is also because this is affecting precisely that very disturbance that we see here. And moreover, the bandwidth is important, as I said earlier. So we can see that up to 100 hertz, we are in the sub-nanometer or in the sub-nanoradian position stability. And it's only when we go to 500 hertz or 1 kilohertz that we eventually reach the 10 nanoradians. So this is a compromise between the probe or the beam getting blurred or being moved on a sample, for example. And then this is always static performance. And in the bottom, I show some scanning performances. So this is a real energy scan taken in one of our beamlines. It's a 3 kilo electron volts done in 3 seconds. So basically we scan the edge of 3 different elements and you can also take time domain analysis on that. And this is one last set of results telling how fast we can go and how the performances get worsened by mechanical disturbances that are added as we go faster. So there are many results, even in the previous ICALEPCS or MATSI conferences. We have a summary in the end. To move on, we are happy with the HD DCM, but we want to go further now. So we are designing the HD DCM Lite, which is a lighter version, a shorter and stiffer version of the original one. And as it goes smaller, it can go faster. And then we have even double-sided the goniometers for additional torque. So it means that we can move, for example, sinusoidally very fast and still keep the quality of the positioning between the crystals. This is an example of the same cumulative power spectrum. So showing the 2 performances of the DCM that I showed earlier. And this is the light version. So we expect to go almost a factor 2 even better because of better plant design or simplified plant design. And in here, in this table, we have the contributions of the systems. This is the performance of the angle that I just mentioned. And it's also saying how fast we can go. So basically on the limits of the encoders, the motor torques, the motor forces, and so on. So how many cycles per second we can expect and what kind of new science opportunities that can give. And then this is basically taken from the same table, and we are saying that when we need higher angular amplitudes, we have to go slower and so on. Guilherme will be talking about this in more details in his poster if you are able to join. Sapoti is another project that has been based on the same ideas, and it's an in-vacuum end station that is meant for simultaneous imaging, diffraction, absorption, fluorescence, luminescence, and also tomography. And let's say the target is that we can get nanometer positioning accuracy with a total stroke of 3 millimeters. And that's not easy, as Xavier just told us, right? Piezo's want to do that because either they are too short in stroke or they are too noisy when they are steppers. And then we designed the same concept. So what runs here in this positioning system is the same architecture that has been developed for the DCM with voice coils. And this is what allows us to do the nanometer performance with larger strokes And it's very short motion, of course. I hope we can at least see it, but it can move the system, the sample, which would be at the top here, so that we can scan in front of the beam. And then this shows some measurements. So our range of 2 millimeters being covered officially with measurements. And finally, the performance within about 1 nanometer as specified. So this should come to life next year. In addition to the DCMs and to the end station, we also worked on mirrors and on the 4-crystal monochromator. So this shows one of our silicon mirrors. This shows our 4-crystal monochromator. All the systems are mounted on stiff granite benches because we need that for the whole architecture of the instrument. And one of the nice pieces of work that have been developed recently in PowerBrick, and we have 2 posters about it, is the kinematics. So it means that we say that we need to move the mirrors specifically, and the system knows what every degree of freedom in the granite base needs to do to get there, essentially. And something else that was also done by our team was migrating the original ensemble solution to PowerBrick, because they noticed some gantry issues between the 2 crystals that needed to be controlled, as well as some bugs in the hardware and software. So I think Leandro will be able to talk to you more about it in another poster on Tuesday. We have also an oral presentation on our hexapod kinematics for Bestech mirror. So here we have an hexapod, or most of you know, and we also replaced the original controller by the PowerBrick customized solution. And this shows I scan in dashed lines. You see that the main axis, it should be a pure rotation in this test, and not only the trajectory in the rotation is much smoother in the customized embedded solution in PowerBrick, but also the parasitic errors were significantly reduced. So we have been able to achieve better performance as we take control of everything that we are doing. And furthermore, we have also arbitrary trajectories being injected from a Python script, and then the control errors in the range of a few microns, even over several tens of millimeters. Yeah. We have also worked on temperature control. So this is also key, thinking as the mechatronic system as an integrated approach. This shows a mirror being cooled by copper braids, which is a specific design that we have presented in the MADC conferences. And then we also start from lumped mass models. And then we have developed an architecture with Compact Rio using an integration with the remaining systems. This is a plant identification showing how we identified and planned the models and are able to close the loop control. And finally, how we get millikelvin performances in terms of temperature stability over several hours. We also have a poster on that about the specifics of temperature control. And finally, we have the tattoo, which has been developed by our software group. We also have some posters about it. It's basic a unit in Compact Rio running in FPGA that is an orchestrator to be able to set multiple trigger signals and also delays and a little bit of logics. And then we can tune and execute high performance experiments either in the end stations or with monochromators or mirrors and so on. So I encourage you to also visit the posters. And to conclude, this is let's say the summary of perhaps 7 years of work, and this is telling us how the DCM that is over here is integrated with the whole experimental set, with the whole beamline. So from the undulator up to the experimental hutch samples and photodiodes and sensors. So the tattoo is a key element in synchronizing everything, and we are also in need of making the undulator and the DCM follow closely together. We are currently working on Kima undulators with a back-off controller, which was taken as a commissioning system, and it was a simplified version of the controller. So although it has functionalities, they have not been implemented first or previously. And we should be migrating anyhow to our Delta ondulators, which is an in-house development. And this poster, I don't have the time to cover it all in here, but I will be presenting the poster on Tuesday. You are also invited to come if you can. So this is basically telling that we have an architecture for the ondulator, which is different from an architecture in the DCM. And if we have a system that is able to perform high motion speed and high accuracy, we also need a good integration. And for that, the first attempt was to take the encoder signal from the ondulator and plug it in as a leader to the follower DCM. And what we see here, very briefly, is that our standalone performance from 7.5 nanoradians, it goes to 58 nanoradians just by plugging it without a very aggressive filter. And this is because there is noise in the signal and there is dynamics from the ondulator. And this compromises the high performance instrument that we have, that is the DCM. And we also discussed the architecture, which was basic FPGA implemented and also integrated with EPICS. So to conclude, I'd like to leave the following messages to you. So we adopted control platforms that are standardized for us, and this has provided us autonomy and allowed us to comply even with the most stringent performance demands for series. We have adopted an in-house systemic design approach that aims at optimizing plants so that we can deliver the best possible control result from the best possible plant that we can deliver. And we have used several modeling tools, toolboxes, and software packages that have been constructively improving over design cycles. And the last message is that beyond the standalone instruments, so beyond the mirror, beyond the nanoprobe, beyond the DCM, we need a holistic approach towards the high performance beamline integration, because we just saw that just plugging the ondulator together, which has not been specified or designed for it, can completely degrade the performance of an otherwise nice system. And these, so the integration becomes increasingly more important, and also keeping well-trained staff with knowledge to handle all that. So there is a lot of knowledge involved, and this needs to be protected. So we have one oral session with Augusto, several posters on Tuesdays and Wednesday and Thursday. So please join us. I'll be happy to answer any questions. I have a final list of references from previous conferences that we attended. Thank you very much for your attention.
Well, thank you, Henan, for a very informative talk. Questions for Henan? No. Anyone?
Perhaps Dominic is saying something, I'm not sure.
If you can stop sharing, Henan, then we can see the
Okay.
Thank you.
Sure.
I have one question. You mentioned that you don't control the DCM with the Delta controller. What is the limitation you identify for choosing compact RIO rather than Delta 2 for that?
Actually, the Tattoo is a package that runs in a compact RIO as well, but it's a different one. So we have one compact RIO that runs the FPGA code and the real-time code for the DCM, and it takes already 95% of the FPGA capacity. And the Tattoo runs on a separate compact RIO, and it just handles, or it can do different things, but it basically handles the trigger signal. So it's a separate unit. So the DCM works as a standalone system on a compact RIO, and that Tattoo is a different compact RIO that orchestrates all the communication between the DCM and the different elements at the beamline.
Yeah, sorry. I was mentioning the Delta 2 controller. Because you identify, you control the DCM with the compact RIO. But why you make this choice rather than using the Delta 2 platform you are also at the Cyrus?
Yeah, the delta tau is simply not capable enough. So we need a lot of the resources that are embedded in the FPGA and in the compact Rio. So yeah, even the real time, I'm not sure. Yeah, when this how the decision was taken, but yeah, I'm totally sure that the delta tau was not capable, even the real time operating system or the FPGA, as far as it can go. It couldn't do it. We started with an XPC from a computer from SpeedGoat, but it was not robust for an industrial application. And then we migrated to compact Rio. I can get my colleagues to give you more details on that later.
So on any of the sample average beam lines, what proportion would you have being controlled by compact Rio for motion, and what proportion from your industrial motion controller, like the Delta?
Yeah, we just go for compact Rio where we need it, really. So it's really every case needs to be analyzed, and from all the mirrors, for example, and so on. We basically always have a compact Rio because it handles temperature as well, and it handles the timing. So we always have at least one for every beam line, but then the number of them will be totally depending on the number of critical instruments that are there. So there are beam lines that have 4 or 5 compact Rios, just because it has a DCM and a challenging sample environment, for example. So there is at least one compact Rio for all of them, many delta taus, and many power bricks, right? And pieces and flavors of specified instruments.
Okay, thank you very much.
My pleasure.
One last question for Henan, or should we move to the breakout session?
I would like to ask just a little question. If I understood correctly, is it true, if I understood correctly, the compact Rio can handle most delta tau applications, but the delta tau cannot handle most the compact Rio? The compact Rio is more performing?
Yes, yes.
Yeah. And it's mostly in computing power and or frequency, or yeah.
Yeah, I think it has to do with memory allocation, a lot of number of ports and so on. So compact Rio is very flexible because you can adapt number of digital signals, analog signals, temperature, right, whatever you want. So we can really customize it so it can be used not only for motion, but even the most demanding motion tasks. So you additionally need drivers and so on, which perhaps is beyond, right? Delta tau already has a lot of it embedded. So it really needs to be balanced. And now with the pool of solutions that we have, we always judge based on performance and costs, what should be taken.
Okay, thank you.
Sure.
Right. Krista, would you mind sharing the first breakout session? I'm going to step out of the room for a moment. Hopefully I'll be back in time to join my breakout room.
I don't know if you guys all can see that. So now it's time for our breakout session where we'll talk about experiences in motion control. I don't know if you all can see in your Zoom application, there should be 6 breakout rooms. We asked for 6, but we will only need 5 in this case. So if you could, if you could find your name then you could identify which group you go in, and then you could go into your respective breakout group. And then in each group we have one organizer where we will pose 3 discussion points where we'll discuss during 20 to 30 minutes. If you cannot find your name in the list for some reason, feel free to join one of the 5 groups as you are. And me, I'm organizing in group 2, and I'll join in after a bit, after I make sure that people have joined the various breakout room groups.
So which breakout rooms are we going to, guys?
I think it should be written in the, your name should be in the group. So you, Brian, I think you were in group 3, if I remember correctly.
Yep. Okay.
Yeah.
Have we assigned the questions?
Yeah, I have them right here. It's just, I'm not sure what happens when I join the breakout room.
It'll go, so.
Yeah, so if each of the organizers could take the 3 questions.
I will join my room. At the moment,
Yep.
I have only 3 people there.
Shall we wait a few more minutes? We have plenty of people in the main.
I've got a
group.
few in mind
And
now. 1, 2, 3, 4, 5, 6, 7.
can you guys see how many are in group 2? I cannot see while I'm sharing, I think.
Group
To
2, there
join
are
to the group,
4 people.
which is the way to join to the group?
You
There
can
should
go
be
to
a
the
button.
You hover with the mouse on the breakout room that you want to join, and that rightmost side of the screen, then you have a join button.
Okay.
I will join number 4. Maybe
Okay.
the host could send us in case people.
Okay. Thank you very much.
So we
number 5.
Okay, so we've still got 18 people not in a room yet. 17. Does everybody know how to find their rooms?
Yeah. If for some reason you do not find your name in the list, feel free to join a group, preferably one that doesn't have too many people in it.
Yeah. Okay.
Yeah. Do you guys have questions?
Do you know how we can join the group icon?
I'm going to my room now.
Normally, Marie should have a button at the bottom more, and it says, I cannot see it right now because I'm sharing my screen, but there should be a division, divisé, or something like this.
Yes. But I can't go myself.
You cannot join. Oh, then we need to ask our staff person here, maybe.
No, I know, I understand. I can join myself here.
All right, people here in the main room, feel free to join the various we have 5 breakout rooms that we'll do discussions. If you cannot find your name in the list, just feel free to join any group, preferably one that is not so full. I will join just in a few minutes after I make sure that our main room has been emptied a bit.
Okay. On your slide, Krista, where they are?
It should be on the filer with Marie, if you have it. Or you take a screenshot of this and then show it up there. I guess we didn't really think of that. So I don't know how to share from the main room into all rooms. Does that work? Okay, people who are left in the main room, feel free to join the little breakout rooms listed on here with the group names. If you cannot find your name on the list, just join a room, preferably one that is not full. Okay, I think I'm leaving now to join the room. Dominic, you're coming with me?
Are we the first ones back? I guess we are. Maybe no one else had put a timer on.
Brian, you should know this. It's always the same.
Hello? I should know what?
You should know that no one else puts a timer. It's only you.
Yeah.
I've organized too many of these. Let's have a look. Let's see. Do we want to close the room? If we close them, will they start again? Have we got our organizer here? Broadcast message from all.
If you close it, I can create it again.
All right, no, I'll just broadcast a message. Thank you. 15 minutes long overdue. Please return to main room. Okay, let's see what response that gets.
Probably not a lot.
Nothing ventured, nothing gained.
I don't know. Is it sent to the? No, it's not even. It was just pop. I thought it was maybe in the chat or so, but no.
Yeah.
Okay, Brian, room 1 is coming back.
Thank you. Okay, so it looks like maybe only half the people have finished. Check the rooms. One's closed.
And the breakout room 5, we were only 2 at the very beginning, so we go back to other rooms. So there is only 4 for a breakout room.
Only 4 rooms.
Yeah, only 4 rooms.
We have a problem?
Well, I don't know. Waiting to see if most people are back or not yet. We currently have 30 participants in the meeting and 50 before we went to the breakout. So I assume there's still some not back.
I can see that the breakout room 1 is still full. Breakout 2, we just finished. They're on a break until 35. 3 is quite unforced. Yeah.
Now in the breakout room 4, they are still busy.
I don't know, Brian, if you had the presentation with the questions. I don't know if you had them or.
No, I think you had them, Chris.
Okay, you want me to send them to you just in case? I don't know, because if you have a look at
for the next one, maybe yes. But for this one, if you share the screen, or do we need to share the screen? I don't think we need to share the screen, do we? We'll just.
No, for now I think we're okay.
If you can see the questions, then perhaps you could ask the questions and get each breakout room's minute taker to summarize the 3 questions for us.
All right. Later or now?
Now.
All right, hang on.
Is that last breakout room still full or? I can't see how to Is breakout room 4 still full? Yes, it's still got lots of dots in. Oh, it looks like they're coming out now, yeah.
I think Mary in the room 1 have a meeting after, so maybe she can start reporting from the room 1.
Yeah, room 1's closed. Okay, so I hope during the first breakout session, somebody manfully or womanfully or volunteered to become a note taker so they could summarize the discussion of their room. And so if room 1's volunteer would care to summarize their discussions, we'd be very grateful.
So can you guys hear me?
Thank you. Yes, we can.
Good. So I was volunteered. So we have a really nice group with representatives from ALPA, Australian Synchrotron, Soleil, and STFC. Quite several interesting facilities. For the first question, applying the mechatronical approach, we discussed the barrier because caused by the organization structure. And the solution, there were 2. One is a personal relationship. So between the engineers at different organizations, when you get to know the people, you work better together. And at the ALPA, I believe, they have the weekly coordination meetings that was proved to be helpful as well. And for the second question, the choice of actuators and motors impeding the system performance, we have 2 examples, if I'm not mistaken. Both of them have, I think, with some vacuum-related challenges. So the motor worked well under the atmosphere, and under the vacuum, there were some conditions. Early testing or consideration early on in the design could have helped with that. And for the third one, we didn't have enough time to talk about the collision risks. There were 2 pretty interesting methods reported back. One is a 3D model based on Python from King James STFC's facility. I think that's a pretty interesting way. I think that's probably one way the digital twin or some of the concepts could really help us in this field. And the other is at a firmware level. So they use the delta tau to linearize the axis and try to prevent the collision at that level. The advantage is it does not rely on the epics, and it can stop the motors whenever it's necessary. So other focus, if I missed anything, please just chime in. Thank you.
Thank you very much. Okay, breakout room 2, please.
All right, that was my room, I think. So as for the first point, the mechatronic approach, we discussed it, and it was especially important to rediscuss, reiterate, and redefine the specifications as the different groups got together. That is, say you have initial specifications, and after discussion you realize these are not possible to do under these circumstances, and you need to redefine the specifications, maybe using based on predictive approaches and stuff like this. As for the second point, we discussed the choice of perhaps using, if you were to use stepper motors, they wouldn't work when you do, for example, fly scan methods. In fact, it would be better to use force type actuators like voice coils, for example, to do fly scan applications, especially when you're going for high resolution, high performance scans. We managed to discuss the third point a little bit. One of us had seen applications where they had done pre-computing workspaces based on simulations, and then implemented it into the power brick. And I know that the Brazilian synchrotron, they were looking into maybe using vision systems, maybe using edge detection. So you detect certain edges within certain distances, and then you would stop the appropriate axis in their tracks to avoid collisions. Yep, that's what I have.
Okay, thank you. And the volunteer from breakout room 3, please.
Brian, have we been breakout room 3? Or?
You were breakout room 3, Maxim, yes.
Yes, okay. I couldn't remember. Sorry.
That's okay.
Okay, yeah, I was the volunteer over there, or the person who was not fast enough to switching off the camera. I don't know, one of both. But okay, I also didn't have the question, so I will just randomly point in the points which we which came up. So we were talking about the application of mechatronics, and luckily we had some colleagues from Sirius who, as we all could see, have already some experience. And the very big point which was highlighted was actually getting trained staff or training staff for the mechatronics approach, so that actually the skills are available. It's not only a question of tools, and it's very important to get the skills and the skill set, and then also, yeah, applying the error budgeting during the whole process. And then we had from Soleil some comment that also they started a bit on the mechatronics approach, and they did something similar a bit to Alba to see and look into different actuators. But all the rest, more or less, who commented, like Diamond, HZB, and Jülich, we all struggle still with the old technologies, more or less, and didn't go yet to the mechatronics approach, like seeing everything in parallel. In our case, it's mostly still unchained, the whole development process. And therefore, we had also some bad experience that some having always individually good systems don't give a good composition at the end sometimes. And then on the question on collision avoidance or detection, we also got the information from Sirius that they're starting to look into vision detection, which is like very interesting for me, to me. And ISIS actually works at the moment a lot on software detection, so that mostly in software it will be seen if there is maybe a collision risk or not, and then it will be avoided. Yeah, so I think that's it for the moment. I hope I didn't forget anything.
No, I think you got most of it. Thank you, Maxim. Breakout room 4, please.
So then I will comment. So about the question 1, was not so much the really coming out, except the fact that I think that still we are not there yet. Also, the structure of how groups are defined and how these are put in different departments hinders, in some sense, the collaboration. I also have explicitly asked also at Alba, but I think that they also told that they are not yet there in sense of having weekly or frequent meeting about between the two kind of groups. For XFEL, I still think that we should do much more than that. Luckily, there is a new group of mechanical engineering that was formed last year, and so let's hope for the best. I think that still we have too much of a threshold in order to use facility things like measurements or metrology labs and so on and so forth. We did not really have examples of where it was clear that, or where it came out that the choice of actuators did not hinder the outcome so much. We just discussed one case where somebody decided to use maybe not the proper technology which would maybe have had easier possible less limitations. And I think that we had some information from Sirius and also from Alba of the handling in one case of 1+1 case of collisions with limits or with signals. I think that there we, at least I see it in our case, that we are really doing not enough, I would say. Unfortunately, we are getting involved much too late, and this limits our possibility to introduce limit switches or any kind of sensors which would be able to be handled, and we should do much more than that we are doing at the moment. We are too much late in the game. That's it.
Finally unmute. The dog was barking in the background. Thank you very much, Nicola. Was there a breakout room 5 or 6?
I think there is no breakout room 5 because we were only 2 and we go in the 4 other room.
Oh, okay. All right. Well, thank you very much for sharing, everyone. What do we have next? We have a break coming up.
Yeah.
Eve, can you remember how long it is?
A 15 minutes break.
Okay, that sounds good. So if we can all be back in the main room at the o'clock. It's just about 1:45, whatever time it is now, depending whereabouts in the world we are. So that would be a good time to take the 15-minute break.
Yeah.
Thank you very much for all your input so far, and I look forward to seeing you all in a few minutes. I'll just be muting my camera and microphone, so the room will still be, the meeting will still be open. I wonder how we'll know if everybody's back. I'll tell you what, if you're back, if you could react with a clap or a thumbs up, I can see on the screen roughly how many people are back.
Are you sitting with the lads then?
Okay. Right, it's looking good. We have quite a few back. Well, I think the second session has a couple of talks on implementation of robotics at some beamlines. The first talk will be robotic pick and place by Laura. Is Laura here?
Yes.
Excellent. And then the second talk will be robot arm holding diffraction detector from me. Are your slides ready, Laura?
Yes.
Okay. Well, we'll give them a minute over because we're kind and generous like that.
Okay.
Oh dear.
Oh.
Okay. Thank you, Laura. When you're ready.
Okay, so can you see my presentation?
Yes.
Yes, we can see your presentation. Sorry, you probably can't see me nodding behind your presentation.
Okay, so I don't know how I can. So, okay. So, well, I'm going to start. So hello, everyone. My name is Laura Minos. Today I'm going to talk about two robotic applications that have been developed at Soleil using robot manipulators. So I'll begin by an introduction. Then I will talk about the two applications that we have developed to carry out powder diffraction measurements and to characterize the magnetic field of magnets. To finish, I will give you the conclusions and the future work. So by a robot manipulator is meant a mechanical structure that is analogous to the human arm in its ability to reach, grasp, and manipulate. On the industries, the most uses of this type of robots is the automotive industry. But more recently, the medical industry has begun to develop robotic applications. The type of task that the robot can perform in industry are, for example, welding, assembly, or maybe painting. And one of the oldest is picking and placing objects. So in a pick and place application, the robot will pick an object somewhere and it will put it somewhere else. So in a synchrotron, the automatic sample changer with robots it's one of the most deployed applications, which correspond to B-complex type. So the automatic sample changer is used, for example, in beamlines to perform macromolecular crystallography or maybe X-ray diffractions. And another type of application, and I think the next presentation is going to talk about, is to use the robot as a detector holder. In this kind of application, the robot will position the detector in its 3D workspace to accomplish experiments. Sorry. And some example that we can find is the Bragg CDI or the Bragg pictography. Well, but the use of robots is not limited to this kind of application. There are also other applications such positioning samples. As we can see in the photo here, there is a tree that it's analyzed. Some years ago at Soleil came up with the idea to further automate beamlines, and it was concluded that the robots manipulators would be a good solution. Therefore, a robotic standard was developed. The standard consisted of setting a brand for the mechanical arm and also for the controller. In this case, we choose a Stobly. And we also setting a software interface in a form of a C++ library in order to facilitate the communication between the controller and Tango. So the purpose of doing this was to have a better operational management, a better maintenance, integrate robots more easily into existing processes, and to make evolutions in application also more easy. So the two applications that we'll talk about in a minute use the Stobly TX260L robot. Since the low capacity, the radius of action, and the positioning repeatability were enough to cover the application requirements. But we can use another Stobly model if we want. So the first application to emerge from this standardization is an automatic changer application for powder diffraction measurements on the crystal beamline. So in the figure, we can see the experimental platform, which has a two-circle diffractometer, which also have two detectors to perform the different kind of experiments. The platform also have the sample store with a capacity of 36 samples. The robot is mounted on a moving chassis, which has the controller, the fluid panels, and the input-output modules. So we cannot see the components, but this is the chassis. So it was chosen to put the robot on a mobile chassis in such a way it could be moved in the case of no use of the robot. So on the video that we are going to watch, we are going to see how the application works. So the application begins with the automatic mounting of the sample where the robot will take the sample to be analyzed. It will verify if there is any sample on the diffractometer with the help of this laser sensor. And if there is not any sample, you will put the sample on the diffractometer. So we can see that. After that, the process, the task of self-centering of the sample will begin. And to carry out this task, the spinner, we're going to do some rotation in such a way to calculate a centroid value with the help of a camera. And once the centroid value is the same for all rotation, the capillary is considered to be in the center. So once this task is finished, we can see here, how the spinner do the rotation, and after that we can see how the detector, the scanning start and the measurement are carried out. So once the measurements are finished, the robot will take the sample and it will put it back to its position in the sample store. So the two first steps of the process will take about 1 minute and 30 seconds. And this allows us to save about 8 minutes, if a person does it. Okay, so the second application is used to accomplish the magnetic characterization of hundreds of models or magnets that compose an undulator. So for this application, the robot is mounted on a pedestal, and the controller, the inputs models, and the electric rack are placed in a bay next to the measurement bench. We can see in the photo that the boxes where the modules are, or the magnets are stored perfectly. And we can also see the tool that the robot used to do the task. So the tool consists of 2 finger gripper and a force torque sensor that it is used to position the magnet on the test bench correctly. Okay, so here we're going to watch another video. So here the robot will take the magnets that it's on the box. It will position it in an intermediate zone so that it can be correctly placed on the test bench. So here we can see how it's placed, and in the in this figure we can see how the module is, the final position of the module on the test bench. So once the module is in position, a half of that we cannot see here, and a rotating toy that we can see over here will carry out the magnetic measurements. So once these magnetic measurements are finished, the robot will take the module to make a I don't know how to say that, to make to turn over the module to be measured by sorry, I lost my idea. So yes, the robot will take the module from the bench. After that, I don't know if you see it, but after that, it will put it back here to turn over the module and then make some measurements of the other side of the magnet. So, and finally, after all the measures are finished, the robot takes the module back to its position on the in the box. So the whole process takes about 50 minutes, but and it's important to say that before it was a person who was in charge to put the module on the bench. But as I say earlier, the magnets are hundreds of magnets that we have to measure. So it becomes a repetitive task for a human. So a robot, we think it's a good solution for this type of applications. Regarding the software, we have developed a robot device which has generic methods for all the applications, such as turning the robot on or off, and other methods that are specific to an application. So to give you an example, the crystal application has specific methods that commands put and get to mount and dismount the sample. And the whole process is managed using high-level scripts, taking the advantage of the Tango bindings that we have at Soleil. So this approach allows us to easily integrate the robot into the architecture used by different beamlines or teams. In the case of the crystal beamline, we use Python to automate the process. And in the case of the magnetic measurements, we use Igor Pro to make the automation. So just to finish, I will give you some conclusions. So we have two robotics applications have been developed using the Soleil robotics standard. This application allows us to carry out measurements 44 hours a day. And I didn't tell you before, but the magnetic application was designed and developed in-house at Soleil, and the other application was developed by an integrator. But thanks to the standard that we have developed before, the integration was very easy. So in the future, we have already identified already 10 applications to automate some experiments using robots. So this application led us to face new challenges, such as collision avoidance, manage more complex environments, and also we have to cover high demands on accuracy and stability. And I finish. So thank you very much. I don't know if you have any question.
Thank you. Any questions for Laura?
Yes, I have one. Thank you for the presentation. Do you have any measurements on current accuracy and stability done by interferometers or some other instrument?
Yes, we have some, but not for these two applications, but because it was not necessary. For this application, we only need repeatability, so it was enough. But we have another application that I didn't talk about it because it's only, it has been installed but not tested. And in the other application, we have made some experiments on stability and accuracy. So the other application is for to make to carry out Bragg CDI experiments, and it's an application to position the detector in the space. But we are not finished, so I don't know exactly if I can say the data or not, those results.
Okay, thank you.
Thank you. We have a minute for another question if anyone has anything. Well, thank you once again. Laura, if you can stop sharing now, we'll get the next presenter ready.
So,
okay, thank you very much. Next up, unfortunately for you guys, is you get to hear me talking again. Let's see if I can prepare my slide. I want to do that. I want to share my screen. Right, can you all see my screen? One yes will do. Thank you. Okay, so thank you to Laura for pointing out that we have a robotic application for holding a detector. RAHDD, robot arm holding diffraction detector. Find the button that works. Okay, so DIAD, dual imaging and diffraction, uses two X-ray sources to shine onto a single sample. The idea being that we have an imaging beam and a diffraction beam. And so we're going to talk today about how we implemented the diffraction part of this beamline. So it's an imaging camera and a 2D diffraction detector. The robot must be moved to any position around the sample. Any is in a question mark. Do we need to be anywhere, or could we simply have a matrix of positions? If you're carrying a £500,000 detector, it requires a very big and capable robot, which must not be a risk to personnel, first and foremost. It must not be a risk to the £500,000 detector. It must not be a risk to any of the other equipment around it. Similarly, it must not be put at risk from any external equipment. It needs to be integrated into EPICS and GDA, which is our genetic data acquisition, which is our scripting and experimental suite software. And it has to have a safety rated PLC for machinery protection, not for personnel safety. So we have three sample positions on the beamline. One carries a tensile torsional stress rig, one is a simple manipulator, and then there's a third station where users can bring their own experimental station. And the robot, as we can see, carries the detector, and custom built table carries the imaging detector. So how will the robot position the detector within an area of the diode experiment's hutch? So it covers part of a sphere, and the positions are all referenced to the center of the sample. We position it on two spheres, typically either 300 radius or a 600 radius sphere. At the moment, we're not putting it anywhere in between. And the arc sector that it has to cover is 0 degrees to 155 degrees. And the detector will typically be above the plane of the X-ray beam. This is a quick system description of the hardware. So it's a Yaskawa MH255 robot controller, each pendant, and the robot itself. There is a collision sensor planned for the future. We've been talking about collision avoidance earlier, but if you can't avoid it, at least detect it before you do any damage. Typically then the experiments are scripted via the GDA user interface, which communicates with EPICS. And we have, in this instance, an end station PLC. And one of the things that this safety-related PLC does is to communicate to the robot when various bits and pieces of equipment are in its movement zone, and that triggers various safety areas. And then also with that, we have PSS, Personnel Safety System, which handles the interlocking to the robot. So when the hutch is searched, closed, and locked, the robot can move at normal speed. We have an e-stop and an enable. So the robot controller contains all the equipment to move the robot in a safe, coordinated manner. Please excuse the dog, she's getting excited. And this includes two specific optional items relating to the safety system. We have a machinery safety board, which allows us to connect functionally safe I/O, and it allows us to connect the emergency stop, supervise various operating modes, and interface with the guarding. And we have the functional safety board, which is certified to category 3 PLD, and that allows us to have safe limit on axis range, safe limit on axis speed, monitoring tool changes, limit the tool speed, and limit the tool angle. And the functional safety board also allows us to specify safety zones. They can be keep in or keep out, and the safety zones can be programmed with the different tool shapes and sizes. So the kinds of safety zones you can have: you must not leave this area. You can have, you must not go into an area, and you cannot cross into a certain plane. And onto the end effector, you can create, using spheres and hemispheres, the tool shape. So what do we have to avoid? And what needs to avoid the robot? As we said earlier, we've got the 3 end stations that can be fitted, and typically we will have 2, and the users can bring 1. So far, we have only used the traditional sample stage. We haven't used the tomography stage. And we have to avoid the imaging camera. So these have to be, the areas that they create have to be specified. And when this translation stage puts the different end stations into the path of the beam, then we have to tell the robot it's a different shaped area to keep out of. So we have defined 15 ranges that are a mixture of keep in and keep out and stay above or stay away from. The shapes of those ranges, we've given ourselves some descriptors so we know what the box is, like the user platform or the KB mirrors. KB mirrors are fixed and the user platform can move in and out. Excuse me. But as you can see, in order for the functional safety unit to manage this zone, it requires a certain percentage of utilization of its onboard processor. And if we were to have all 15 zones operating at once, we would more than saturate 100% of the CPU. So one of the reasons we have a functional safety PLC is so that we can have safe communication between the environment and the robot so that the robot knows which zones are active at any one time. So the input from the functional safety PLC describes which zone is going to be active at any one time. Similarly, the robot has to provide digital outputs to the functional safety PLC so that if the robot's in a certain position, the functional safety PLC can prevent movement of the main translation stage, which is a very powerful stage and can do an awful lot of damage. It'll prevent movement of the imaging camera stage, and it will provide an output to say that the robot is in its home position and therefore everything else is safe to be moved normally on the beamline. So we had to describe to ourselves and to the robot the areas to be avoided at the certain stages. And one of the things that we also do with the functional safety PLC is that for stages that can hit the robot or the robot must avoid, we provided a second encoder to those stages, which is an absolute encoder, in this instance an SSI encoder, which doesn't communicate to that motion controller, but communicates to the safety PLC so that the safety PLC knows where these other pieces of equipment are, rather than relying on range switches to give us that information. We have 3 modes of operation. Automatic mode, which is only available when the hutch is fully searched and locked. Position requests come via EPICS onto one of 2 radii and can fit in any 5-degree increment. And we have to rotate the detector face to be a plane to facing the sample. We have an automatic safe speed for doing checks, position requests via EPICS, and this movement is only allowed if the PLC will allow it, and the robot can only operate at safe speed or slower. This is key access controlled and is only available to trained Diamond personnel. And there's a teach mode for programming and recovery of the robot system, only available when the pendant is attached to the robot and the pendant is locked away with a safe key that only the PBS and principal beamline scientist and trained staff have access to. So here's a quick diagram of the layers of control. So on the one hand, we just check that everything is within safe limits, and the robot communicates to the safe PLC, communicates to EPICS, communicates to GDA. We have status communication, status and alarms. Then we have a setup mode. We get basic robot safety, status going to GDA, testing the interlocks and the safety input. And then when we're doing the full experiment, Then GDA sends requests go to EPICS. EPICS has to go via the PLC in this instance, and I mentioned why in a moment. And then the robot does what the robot has to do. Covered the functional safety unit earlier. We don't need to go over that again, keeping one eye on the clock. So here's an example of the EPIC screen, which displays current position of the arm, the robot coordinate systems, X, Y, Z, rotation about X, Y, and Z, detector coordinates. So these are permanent status displays, and then we request a position, and when the position of the new alpha, beta, gamma and detector coordinates are set, we then move them. We then request a move, or we can tweak those positions slightly. So there's a move to a new position, and then there's a slight tweak. And then we can adjust the face of the detector slightly to avoid or to do the experiment twice, so that we can offset the gaps in the array of the CCD detectors. So the user FX interface with commands for operating the robot, we can request position, we can request to adjust the position, we can request the sample position, so that if the sample is moved, the detector can adjust. The center of the sample has moved, we can move the sphere around to compensate for that, and we adjust the face. And like I say, that is to so that the X-rays hit different parts of the detector at different times. We also have the ability to send direct commands to the robot. So instead of these initiating a software program, then they direct commands to the robot, force the robot to go to a safe position, rehome the robot, which we don't do, only very trained personnel do that. A detector servicing position, we can stop the robot, we can pause the robot, or we can make the robot recover to a safe position by direct command rather than via the EPICS experimental commands. We use a Omron NX PLC. Bear with me a moment. Set the time of, I'm now eating into our 5 minutes of questions. I shall move on quickly. So EPICS displays these positions, and I don't know if you've come to the slide yet. These are the variables that are read-only, so EPICS reads these positions from the detector. Then we have read-write variables that are transmitted to the detector via the PLC. And we're using an Ethernet IP interface. And the reason we have to use Ethernet IP is because the safety system uses Ethernet IP, and the robot won't allow us to just use a normal Ethernet connection. And so in Ethernet IP, we have to construct our variables as packets of bytes. So EPICS will send an instruction to the safety PLC. The safety PLC will just deconstruct those into bytes. Those will get sent to the robot. The robot will then have to repackage them together into either a command or data, and it does that as a system job function, which is a low-level system function, and these were programmed for us by Yaskawa. Typical sequence of operations. Move to a command position, check where we are, overwrite the position if we need to, and then when all of that has been checked and tested, we'll then actually move to the position. So this was several years of work from very many people, and of course it was interrupted by COVID. So there was basically 18 months of very limited access to Diamond. We were shut apart from the macromolecular crystallography beamlines using their pick and place robots to load thousands of samples and take data which ultimately helped in providing data for creating COVID vaccines. And so very little effort was able to be done on site, but we did actually get on site to complete the robot, and we have had first user. And this is an example, unfortunately it's imaging, not diffraction, of a tomography experiment on that end station. So thank you for your attention. And we do have a minute or two for questions. Any questions?
I have one. Were there any new challenges with respect to previous experiences with robots for this one?
Beamline I-14 had used the robots for positioning detectors prior to this one. It was an older robot and didn't have the same functionality. For us, the new challenge was interfacing with the functional safety unit, which, because we had so many zones to keep out and so many avoidance zones to program, we couldn't just program a model of the beam and then let the robots move around it. That model had to change, and to change the model safely, we had to use functionally safe inputs. And then, of course, that hit us with the hidden challenge of having to construct all the information over Ethernet IP and assembling and disassembling the packets. Now, assuming this puts them up in order, Maxim and then Yves-Marie, the next two questions. Maxim.
Yeah, just one short question about the positioning stability of the detector afterwards, because I was wondering if you have like the arm reaching out quite far, then you might be, it might be a bit shaky, let's say. I don't know how heavy the detector is. So do you have any information on
that? One moment. Share again. It's just in not presenter mode, but you can see we did some stability, and you can see that the stability measurements show us at the end of the effector arm with the servo motors off to be, depending on whether it's X, Y, or Z, plus or minus 4 microns. I'm colorblind, so I couldn't tell you which that one is, down to plus or minus 2 microns, and for one of the other, we see X 4 microns, Y 8 microns, and Z 4 microns. And this repeatability and stability was measured with capacitive sensors, with the robot at maximum extension held against with the capacitive sensors mounted to a jig. I'll leave the slides up just in case there's another relevant question that I can nip to a slide and have a look. Okay, who is next? Was it Krista?
It was the same question.
Okay. Oh. All right, thank you. Any more questions? All right, well, thank you very much. I'll stop the sharing. Krista, if we can move over to you to show us the questions for the next breakout session.
Will do. I'm going to share the... Just a second. So now we have our second breakout session of the day, and we'll be talking a bit of experiences in robotics. If you would go into your respective groups.
Are they the same groups as last time, Krista?
These are the same groups like last time. Feel free, if you deem that the groups are a little too big, to go to a smaller group to make them a bit even. I think last time by chance we had one group just didn't exist for some reason, and then we had some groups that were much bigger. So if you feel free to, if you feel that the group is slightly too big, go to a smaller one. I'll leave this open for just a while. And I think these are the 3 questions that we're gonna discuss. I'll go back to the group.
Okay, leave the questions. Oh, okay.
Yeah, leaving the questions.
Okay. If we all make a note of the questions, or at least the hosts.
The host, will you let me know when you have copied the questions?
Yeah, I've got mine. Thank you. And then we can go back to showing the who goes
I
where.
don't know how many we still have yet in the main group. I can see what I'm sharing.
Okay, still showing 20 people, still to find a breakout room.
So if you don't know it already, there's a little button in the down bar that you click it and you can go into the subgroups.
Okay. We come back in 20 minutes.
20,
roughly
if we like.
20
Okay.
minutes.
Yeah.
Yeah.
To have the 10 minutes to share the discussion on, because we are running late.
Yes, okay.
So, okay.
Okay. How many are we in the main group?
Still 15 at the moment.
Right. Guys, find a breakout group. If your name isn't on this thing, feel free to join any group that don't have too many people in it.
Okay, we've just had a little message from Nils saying his presenter will join us in 30 minutes. So should we swap the order of the last 2 around? Sure. Or should we wait 30 minutes for the Beckhoff talk on maglev?
You want me to go first and then we wait for him?
It's a question.
Yeah, I'm fine with that. If you
okay.
I'm okay. Yeah. All right.
I'll just
I'm gonna go into my little group now, I guess. See
okay, yeah.
Everybody in there. Oh, we're quite many in the main group still.
Still 13 in the main group, yeah.
Mm.
Right, I'll head to breakout room 3. So, Thomas, you're also expected in breakout room 3. Thank you. And Augusto, join me in room 3.
All right. I think some of the groups are not done yet, so we're just waiting for them to finish up. Feel free to grab a cup of coffee or whatever you guys have for the breaks while waiting. I think it's still going to take a few more minutes. I don't know how the other groups are full. I can see what I'm sharing.
I reckon only the group of Brian is still discussing. All the other groups have joined back. Right. Maybe we could ask Eve, do you want to?
Want me to go in the group too?
Yeah.
Okay, I go.
Because we are, I think, 20 minutes late.
Yeah, I pushed my group to finish a little faster than usual, so it's a bit time constrained.
Room 3 is coming. I don't know if somebody is missing. No, it's okay.
No. So who's chairing? Crystal?
It's muted us in again. So how many breakout rooms did we have this time?
I think the same.
Four. I
Four?
think the same 4 room.
Okay.
I noticed we had one very big group and then a few small ones. That's okay.
Okay. All right. So I propose that we start this time with breakout room 4. Would you like to put forward your note to take care?
I took the notes. I mean, we have mostly, among us, we have mostly pick and place robots. I think 1 at Alba, 2 at Sirius. I think also ISIS has at least 1, most probably. At XFL, we have at least 1 robot, Stoibli, doing detector placement. The project is, as far as I know, not yet finalized. For the communication exchange, we had in one case at Sirius Ethernet plus Delta Tau in the native communication. At Alba, digital signals are exchanged among entities to know where to go and where to do. For XFEL, I think that the project had started and then most probably was put on hold due to pandemics. At that moment in time, we had basically a signal for the hatch closed and searched and locked to allow the movement at all, but the rest was at that moment in time was based on Caribou motion control. So basically, Caribou would know everything. Hopefully, would also maybe forbid people clashing into each other, but don't know whether it was really put into place. For the collaborative robot, it seemed that no one was really thinking that there would be any interest in the institute. What I have reported is something that it has been done in the tunnel of XFEL, so in the RINAC, and they have since quite a number of years something that is called Marvin, and this is a robot on wheels that is remote controlled and has sensors to stop any movement if humans approaches. It's mainly used for monitoring of the radiation doses and this kind of things. Most probably it is also able to do visual inspection of machine elements, but not much more. In the photon tunnels of XFEL, there are also something that are not really robots and are only able to be permitted to move while no one is in the tunnel. These are basically cameras placed on rails, and these have been used at the very beginning of time to do kind of virtual tours of the status of the tunnels. I'm not fully sure that they are still in use because they were a internal project of a person that has left us. So I'm not sure that they are still maintained, and also the issues of electrical safeties maybe would need to be explored.
Okay, thank you. Breakout room 3, please.
Hello. So,
yeah.
Oh, hello. Yeah. So, from using about robots, most people seem to be employing this. It's called pick and place sort of sample changers. We use quite widely. There was couple of places where they've used a robot for positional diffraction detector. That was at Diamond. At ISIS, we also have a robot arm that holds a camera for an imaging beamline in place. But we don't, that's controlled by humans. We don't control it automatically at all, as it doesn't need to be done very often. So that's run that way. There's also some use of hexapods for doing things like positioning in mirrors, which are being used. But most common use was, as you say, pick and mix sample changer. Though in some cases there might be multiple stacked sample changers that are being done. For handling the environment, the robot, Brian mentioned about functionally safe inputs to actually make sure that the devices are actually, you've got the right commands and you verified that things are working properly. I think that was the only thing that really came up on that sort of side for us. Cobots, there's not, I think, a lot of use going with them at the moment. There's some interest in them that they might be able to use. I think was mentioned that there's a project, they might be used in kind with the European Spallation Source, investigating using how this might help with in some areas with safety requirements. There's interest sometimes from scientists that they could use cobots to help verify what a robot is doing. But yes, not a lot of use of cobots was mentioned at the moment.
Thank you very much. And breakout room 2, please.
All right. Again, for the type of robots, again, pick and place is a common theme that comes up. We have them at Soleil and we have them in Brazil. Not so much used in the radio telescopes, though. In Brazil, they had planned to use them for detector placements and possibly within precision placement. And we're talking within the micron range. That is yet to be seen, but it is in talks. Number 2, again, serious. They're considering maybe something vision-based could be of interest, but again, it's still just speculative as so far. Now, number 3, collaborative robots. There's nothing so far. I mean, the question came up in what applications would they be interesting. Now, I did remember in Soleil that we have taken up the discussion, but I didn't remember exactly what applications that we had in mind. But to handle that, to handle collaborative robots, we discussed freeze upon entering the room kind of a thing, that once you enter the room, at least they wouldn't be allowed to move, but it all it all depends on the application, and it would have to be discussed when the application is known. That's all I have for group 2.
And from group 1, please.
I can do it. In group 1, okay, there is in the facility represented there no real robot application in the roadmap of the facility, apart Soleil presented the one presented by Soleil, by Laura. So on the traditional one, that application that we can find for crystallography beamline. So it was a short discussion, but around the vision-based system, some question appear about experience with this such approach, in particular with vision in where there is a lot of dust. So it was proposed to extend the discussion on robotics, but more largely on motion control or on feature around this kind of system in a Slack discussion or something like that. So probably it's a topic that we had a few years ago, and we create the MOCRAF website. Maybe it's a topic to renew.
Okay, thank you. Could I ask that all the note takers try to not scrumple their notes immediately the meeting ends, but if they can type them up and forward them to either Eve Marie, myself, or any of the other MOCRAF organisers. We will have been swamping you with emails, so you should have our addresses. And then the notes from the individual sessions can be stored along with the presentations for the workshop. Which brings us to the final session. I think we do magnetic levitation presentation from Beckhoff and collision avoidance from Soleil. Is the Beckhoff presenter ready and available now?
Yep, he's here.
Okay, so excuse me. If you're ready, then 15-minute slot with 5 minutes Q&A, please.
Mm-hmm.
Okay.
Let me start the presentation.
All right.
Yo, can you see everything?
Yes, thank you very much.
Perfect. Yeah, then let's start. Thanks for having me first, and thanks for talking to you a little bit about magnetic levitation, how this can be realized in the industry, and how we as Beckhoff do that. Quick note to myself, my name is Johannes Beckhoff. I'm working for Beckhoff Automation now since 3 years, I guess. And I'm working in the software development of the X-Planar, how we call this our product, which uses the magnetic levitation, and also working a little bit in the product management for the X-Planar. Before I start talking about the X-Planar and magnetic levitation, let me give you a short introduction to Beckhoff Automation. Some or many of you already know us, but we always like to repeat what we are doing as Beckhoff Automation. So yeah, as Beckhoff, we are automating machines and also physics experiments all over the world. And we're doing this with PC-based control, which is our control philosophy, which means that we have one central PC, which our whole control. This PC is then equipped with our software Trinket, where everything takes place. And yeah, with this philosophy, we offer a broad range of control components, which you can see here from the left to the right. So of course, we are developing and selling you IPCs, which we use for our control. They come in all forms and performance classes. So no matter if you want a low performance IPC with a small Atom CPU, or if you want to go to the server PC with more than 40 cores because it's a dual socket Xeon CPU, which can also do real time and control whole machines, you can get that from us. Same goes for the IO components. So whenever you want to collect a signal or give out a signal at your machine, this is what we usually can do best because we have our, I think over 2,000 IO terminals. So usually any signal you can imagine can be collected by us. And we even offer, let's call them a little bit scientific IO components. So if you want to collect data with up to 50 kilo samples or even higher, 50 kilo samples per second and resolutions down to 24 bits, you can do this with our IO components. Of course, another part of the automation technology is the motion part. So motors, doesn't matter if it's stepper motors, servo motors, or any kind of special motors like the X-Planar, so any kind of special movements. We are developing and selling them as well as the drive systems. And of course, last but not least, our Trinket software, which transforms our IPCs, which are usually usual PCs where Windows runs on, which transforms those PCs in real-time control, real-time controllers. And last but not least, beneath all those hardware products, would be hard to sell them if we didn't have our whole sales and support team. So over the world, over 1,500 experts, means sales and support engineers, work for you, support you, sell you our stuff, so you can use our technology as you want. This is just a really easy example for how our control philosophy works. So here we see a simple CNC machine, not too complicated, but still a good example, because there we have our controller, so usually an industrial PLC from us. working with a panel together to display some things. On this PC, our real-time software Trinket runs, and this Trinket then controls every aspect of the machine. So no matter if it's the bus terminals or collecting data, collecting sensors, and even the drive technology. So all the motion programs, motion programming, all runs on the same software, runs on the same IPC. So we have the central intelligence here controlling the complete machine. And therefore, so as a field bus, we are using EtherCAT, which is also a invention by Becker from 2003, which is actually the fastest industrial field bus. And so if you want to collect data within the range of a few microseconds, no problem at all. This is all done by EtherCAT. Here you can see our general example where we are used. This is a typical machine in the industry. In this case, it's a machine for the mounting of window profiles from Schirmer, which is a company here at our hometown, which was one of the really first customers 40 years ago of this company. And beneath those classical machines, we are also used in many other projects, for example, here in windmills. So we estimate, our customers estimate this, that 50% of the Chinese windmills are automated by back-off control technology. And because China is producing about half of the world's windmills, we can say that 25% of the worldwide windmills are somehow controlled by us. So whenever you see a windmill, there's a 25% chance that back-off technology is used therefore. So this is something completely different compared to a normal machine. Where some things are produced. And of course, we are also used in the in physics experiments here, for example, in the X-FEL in Germany, where back-off, one example where we are used here is, I think that we are used to control the distance of the undulators. So the undulators, this periodic structure of dipole magnets, which is then built around the electron beam, so the electrons start to wiggle and oscillate so they can radiate synchrotron radiation. And their back-off control technology is used to control this 500-meter track of magnets, where each magnet has 2 servo motors, and you can imagine that there are really high demands on the synchronization of all those magnets. And this is no problem actually with our PC-based control, so we can do this control the distance of the magnets of our servo drives, our PCs, and especially with Trinket and EtherCAT. Another example for scientific automation, as we call it, is here the Grand Magellan telescope, which is not built right now, but I think it should go online at 2029, so it's still some time. This telescope, you may know this better than me, maybe. But combines here 7 mirrors combines those 7 mirrors into a singular optical system, which then, so a singular mirror, which then has a total diameter of 25 meters. And there, our PC-based control, and especially EtherCAT as field bus, will be used to synchronize our 3,000 axes together. So those axes then are used to rotate this whole tower, or for example, adjusting those 7 mirrors so the desired optical system is accomplished. Here's just another build, another picture from this. Oh no, this is not the Grand Magellan telescope. Sorry. We also used here the Very Large Telescope, another observatory, the observatory ISO, also placed in Chile, and they also, so this already exists, but this telescope still has many upgrades, and many new astronomical instruments are implemented there, and many of those new astronomical instruments are automated with our PC control. And there especially they use Trinket 3, so the newest version of our Trinket software, as a general control software for the whole infrastructure. Because with Trinket you can do PLC, NCPTP, and for especially for them interesting C++ programming in real time, and also OPC UA function of Trinket, so you can communicate from controller to controller. Here's another build of this Very Large Telescope. And last but not least, last project I want to present you is the LIGO Observatory, which also uses our technology to detect gravitational waves. And there we are, for example, used to control the 2 and 4 kilometer long interferometer arms so that the laser is stable and the laser is as desired. And there we are also used for, of course, what we can do very good for monitoring and diagnostics of the complete facility, so normal housekeeping. And there I think it's really interesting that they also use EtherCAT and or IO terminals for the data acquisition. So that, yeah, it just shows me that even EtherCAT is performant enough and fast enough to, yeah, collect a lot of data from physical experiments. Some business numbers: our headquarters is in Ferl, Germany, so in a small town in the western part or northwestern part of Germany. But in the world, we are presented in subsidiaries in over 39 countries, in over 75 countries. We have any distributor or partner. So usually someone's near you to sell and support our technology. We have over 5,000 employees. More than a third of them are engineers. And this year, we think that we will cross the 1 billion euro revenue mark. So we expect a revenue of about 1.15 billion euros, which is quite nice because that would mean that we grow by 25%, which we are really happy about. Going to the magnetic levitation. So enough about Beckhoff General. Here in the background, you see the explanar, so rendering of the explanar. But before I come to the explanar technology, I want to tell you a little bit about other approaches, how to let magnets fly, which are already used in the industry. So there are different approaches. And the first one is the classical hoverboard. What we do in the hoverboard is not too complicated at all. So in the mover, I will call the moving part the mover in the following slides. You have rotating magnets, so permanent magnets which simply rotate. In the stator, you have a copper plate or any other diamagnetic material. And what happens there is that by those magnets rotating, they induce an eddy current in the copper plate, and those eddy currents then create a repulsive force against the mover, so it's flying. This is really easy and also have some good arguments because you can generate strong forces with that. I mean, there are already hoverboards which have the size of a skateboard, for example, and can transport humans for a short period of time. And of course, the stator is really simple, so it just has to be a copper plate in this example. But there are some problems if you want to use this for the industry, because actually the moving part is the part which needs the energy, so it needs a cable or any kind of battery, and the cable means that the area which we can fly over with the mover is limited due to that cable. Another thing is that we have mechanics in the mover, and this is not the best thing because mechanics tend to fail earlier than electronics and have to be exchanged earlier than electronics. So usually we want to reduce the mechanics in such systems. And we have a really high power consumption, and due to that high power consumption, this copper plate gets really, really hot, which then means it's not suitable for all industries because temperature is always a critical thing. Next approach is really easy approach, but it's still used by some companies. So there's one product on the market which exactly uses this principle. It uses the interaction between permanent magnets. So we have permanent magnets in the mover, and they don't do anything, though they are, they don't move. In the stator, we have permanent magnets as well, which are moving up and down or rotating or moving from side to side. And you can adjust the permanent magnets in the stator in such a way that the mover is levitated. Again, with this principle, you can generate quite strong forces, but the control is super complex because you can imagine that there's no real classical algorithm which can catch how to adjust the stator magnets so the correct force is generated on the mover to control the mover. And again, the mechanics in the stator are really, really, you have mechanics in the stator which we want to avoid if possible. And the position feedback here is really hard to realize because you could do this with cameras, but then again, cameras are kind of complicated if you want to make it in general industrial project industrial project, because often in the industry you have dirt in the air or machines produce dirt, and so cameras may not work as intended. Another thing which is used in most of the cases is the planar reluctance motor. So you have coils in the mover. Again, the mover is the active part here. You have an iron comb structure in the stator. And here, just as for a stepper motor or a reluctance motor, you energize the coils in a mover so that the mover is attracted to the desired spike in this comb structure. And as you can imagine, this system, as it's all, cannot do any levitation because it can just generate attraction forces. So we have to do the levitation due to air bearing. With this principle, you can generate a really high precision. So often, really high precision positioning tables are used with, are built with this principle because you can go in the precision region below 1 micrometer with this. But again, we have the problem that the mover needs a cable supply because the mover is the active part. And of course, we have compressed air, which may suit for some industries and for some experiments, but not for everything. Because if you want to tell a pharmaceutical company that you blow air in the environment, they say, nope, I won't do that at all. Here, last example before I come to the explanar is the superconductivity, which you may all know. And again, there's one product in the industry using this. So here you have a superconducting stator, permanent magnet in the mover, and once you cool down the stator below the critical temperature, the mover will levitate in the height it was when this critical temperature was when the temperature goes below the critical temperature, and then you can simply move the stator around to move the mover around. And you can see that you don't need any control of the mover because once the mover is levitating and in the field of the superconductor, you don't have to control it at all because it just stays there. But still, you have a very bulky construction here in the stator because you need the superconducting material. You have to cool it to really low temperatures, which is also a problem in the industry. And you have to move this bulky construction, so with a whole cooling cabinet and everything, from left to right and front and forth. And so this system just has really pure dynamics and may not suit for everything. So in the explanar, how do we do this? We use the Lorentz force actually. So what we do is that we have coils in the stator and we have permanent magnets in the mover. And with this principle, you can imagine that we can energize our coils in such a way that we let the permanent magnets of the mover fly. This sounds very easy. It's kind of a little bit more complicated, especially in this case, I drew the coils with an iron core. Unfortunately, we cannot use this iron because the attraction force between the permanent magnets and the iron would be much higher than the repulsive force between the currents in the coils and the permanent magnets. So we have to get rid of the iron. So we have here ironless coils. And with this principle, we can let those magnets fly. Really good thing about this, the mover is purely passive. So we don't have any electronics, just magnets in there. We have a really modular principle. So when we want to do this in a large area, we just put more coils to the left and to the right. But still, a problem here. So we can still carry weight. So on a 12 times 12 square centimeter plate, we can carry 2 kilograms. But compared to the other concepts, this generates the smallest forces. And of course, again, here you can imagine that we have really high requirements for the control. So to energize all those coils simultaneously correctly in such a way that this mover is controlled in a nice way. So when we go a little bit deeper into the explanar design, you could imagine, okay, we put coils in the stator. So we take many normal coils, as you can see it here. So this is a drawing of mine, so it's not really accurate, but you can take many small coils, put them in a stator and try to energize them in such a way that the mover is flying. I can tell you from experience, that's really complicated because it's complicated to know how should I energize this and the other coil and all the coils in combination so that the mover is flying. So we're doing a trick, and instead of normal coils, we are using rectangular coils. And the trick of those rectangular coils is seen here, because if we see the rectangular coils just as straight conductors, so we neglect the end traces, we can simply calculate the Lorentz force generated here on this magnet array, for example. So we see conductors in the y direction and also a magnet which is extended in the y direction. And we can assume that this magnet, especially here, is only generating a z field a magnetic field in the Z component and in the X component. And then we can simply calculate the Lorentz force because we just here have a current in the Y direction. And we see that the resulting force on this magnet array just has an X component and a Z component. If you do this for the other direction, so you take conductors and magnets in the X direction, it's the opposite. So here we can only generate force in the Y and in the Z direction. And this really helps us in our control because now it's easy to look how should we energize the coils in such a way that we want the mover to levitate, because we have magnets and conductors in Y direction, which can only generate an X force and a Z force. And we have magnets and conductors in the other direction, which can only generate a Y and a Z force. So what we do in the X planar is we take conductors in the X directions, we take conductors in the Y directions, and we do the same thing for the magnets in the mover, X and Y directions. And now it's simple, because if we want to move in X direction, we simply energize our Y conductors and the mover moves in X. And if we want to move in the Y direction, we do the opposite thing. We just energize our X conductors. And for Z conductors and for force in Z, so for levitating force, we can, we have to energize X and Y as well. So this really simplifies our whole control structure. And this is how we can, grab this whole energizing of the coils in normal algorithms, which makes it much more easier for us. Once you have this, you only have to take care of the position feedback because you need to know where the mover is. And there, the good thing is that the magnetic field of the mover is much, much higher than the magnetic field of the coils, because the coils don't have any iron. They don't create a big magnetic field. So we can simply measure the mover magnetic field, and we can do this, or we do this by Hall sensors. So we just put Hall sensors below the coils, and then we can measure the magnetic field of the mover with those Hall sensors, and we know where the mover is. Yeah, if we take this principle, so this is a really simplified principle of our system, we can put that in a product. And when we put that in a product, it looks like this on the right side. So this is our X-planar stator. So this is our drive, which is on the floor. We call this the X-planar tile. This is because this fully integrated drive has an area, or covers an area of 25 times 25 square centimeters. And what we can do is we can put those tiles and put them next to each other and form an area with that. And in this area, we can move a mover wherever we want. We can move it freely in X, freely in Y direction, tilt it, let it rotate, do whatever we want with it. And cool thing about this tile is it's fully integrated, which means in our words that it integrates all necessary electrical components. So this tile has a power supply, the position feedback I just mentioned the slide before, the power electronics, and of course the stator PCB. Here, this really upper layer where our coils are, where our rectangular coils are. And as I said, we can take multiple of this. We can take multiple of these tiles and just put them together to form a larger area. So here again, on the left side, you see our tile.
Sorry, Johannes, we only have 20 minutes left before the conference has to end. And we've got one more speaker. It was a very interesting presentation, thank you. If you had one more slide to talk about, which one would it be?
Yeah, it would be this one. Okay, so we have our tile and our mover. And then we just think about the whole structure because our system layout is very lean. We need our tile, we need our mover, we need an industrial PC from back off. We need the Trinket software with the X-planar software on it. And what we then just only do is we connect our PC with EtherCAT to the tiles, and we can just daisy chain the EtherCAT connection between different tiles. And this is everything you need to let this X-planar mover flying. And when you have this, I can just show you a random video without anything. So this is how it looks like in the end. This is just one single mover levitating, tilting, so we can control it as we want. And of course, we can take many movers. And when we take many movers, it looks like this. So here we have multiple tiles, multiple movers, which move freely along an area. So we can transport things from A to B. We can even process things on the mover because we can rotate and tilt it and make movements in 6 degrees of freedom, which brings very new features and free features to the machine builders and our customers. And then that's it. If I don't have more time.
Thank you, Johannes.
Thank
Unfortunately,
you.
we have no time for questions. We have one more presentation. It's a topic we've discussed before on collision avoidance. Krista.
All right, we'll try to be quick. A second. All right, so I'll be talking a bit about collision avoidance systems in Soleil. So I have a poster session on Tuesday, that's the code. So what are collision avoidance systems? That is pretty self-explanatory. It's basically how to handle collision risks with motorized systems, particularly in violated or overlapping workspaces. And this image I have there is too simplified and generic, and I'm not actually talking about cars. I'm talking about motorized systems of any kind, really, robots or anything. Now I will be talking about static collision avoidance systems, and our definition in this paper and in this presentation, that basically means that we use proximity or touch-based sensors and with PLC controller configurations. And we have also something called dynamic collision avoidance systems, where we actually use 3D models and encoder feedback to avoid collisions in some kind of algorithm in the controllers. Now, since of the time constraints, I will be focusing more on a dynamic collision avoidance systems on the Mars beamline that we installed last year. I'm speaking on behalf of Jean-Luc Giorgetta, who work in the mechanical engineering group, who helped us, and Simon Bouvel, who we used to work in our group. So in 2018, the Mars beamline, they made clear that they want to create a 2D detector capable of doing SAX experiments, that is basically small angle X-ray scattering. And they want to use that with a 2D detector, basically holding a very heavy detector and moving in quite big ranges, moving it basically 62 degrees and moving it in the range of a meter or so. Now this presents a bit of a problem. It's installed in this is where it was installed. So basically we have a system that contains with moving in X direction. S direction for us is in the beam direction. Rx is moving in that particularly in a rotary direction towards the X. And we have two axes called the TX and TZ beam step. Now the TS, and RX axes are for the detector support that will do the big movements, heavy weight, high resolution. And those are the three axes that puts the system in danger of collision with its surrounding environment. The TX beam stop and TZ are basically beam blocking, and they are, even though they're using the same controller, they're not used in the collision avoidance system. So early on, we had to do our selection criteria based on what motors we had. We had 4-stepper motors, basically standard, and one high-powered brushless motor, a lot of current, a lot of voltage, and we had to be capable of a continuous anti-collision avoidance calculation to avoid colliding our system with its environment. So we use power brick, Delta Tau power brick LV. With a GeoMacro driver to handle the high-powered brushless motor for the detector in this particular control configuration. So, how do we go from the system 3D model to building a collision avoidance system? Now I can just briefly mention that building a dynamic collision avoidance system is part of a comprehensive approach of our group to build a global and a generic approach to avoid collisions in Soleil. We have static systems, like, for example, Puma nanoscopium, that is written in our paper, and dynamic, that is in Mars and Ultras. Now this one is Mars. Now, from going from the system 3D mode to the collision avoidance system, for us it was roughly, we needed to work with the mechanical engineering to go from there to here. And we identified that it was roughly a 5-step process. Now, we would use the 3D model that was given to us by the mechanical engineering group. Usually, we would ask for a simplified model. We don't need every nuts and bolts, and we only need the models that are in danger of collision. We would separate these into separate solid work files, identify the kinematics, and write them down in this case an Excel sheet. We'll take these 3D files and the kinematics, put them into a MATLAB simulation, move it about a bit, and you can see here that this is the movement of the detector, and then this little, I think that is purple, I think. That is the environment that is at risk of, that's a sample that is, we have a risk of colliding with. So using these MATLAB simulations, we would basically try every single point of our TS, TX, RX movement to find any and all collisions. And basically, first of all, we will map all collision points in a data file and generate equations in this particular form. From this, we could generate an algorithm that is scalable to the number of axes that we are using. In this case, we use 3. So we would use 3 axes. That means we have 3 x1, x2, x3. And we have in the number of boundaries we would bind up in the actuator vector space would correspond to each and every single equation. It seems complicated maybe, but it becomes quite scalable if it is done in the right way and if you don't do too many boundaries and too many actuators. And we will basically implement this algorithm into the controller. Now, without bothering too much, I'll go into the results. Well, this is just showing the real system side by side with the simulation. You can see now we're going 3 times the speed, because it would take forever otherwise. And you can see the risk of collision is the blue shape colliding into the purple shape. And now, eventually we did a mock-up in a styrofoam to see if it would work. And now the image to the left is with the anti-collision system activated. The one to the right is not. So you can just see with this exactly same movement, and we had measured it up before. And this is just an example, and it was to reassure ourselves before we installed it, it actually worked. As you can see, the one to the left, it stopped. The one to the right, it collided into the area. And this is also, this is us trying to move the 3 axes continually to see if we even could collide with the system. And the system now we have a relatively complex workspace. Now it will not allow us, no matter what we do. And it is completely dynamic, the workspace, in function to our encoder feedback. So this is a system after it has been installed into Beamline. You can see this is the detector, and this is the sample stage in which we run the risk of collision with. So it is installed into the Mars Beamline and is today operational and in use. So in conclusion, the dynamic CAS system in Mars is functional, and it proves consistency from the 3D model environment to the real world control implementation. And this particular installation, it actually complements static CAS systems, which means that it would complement if we were to install barriers, limit switches, and stuff like that. They are not mutually exclusive. We can install both if we want to really make sure that nothing ever collides. This project, it shows a good example of where we had to collaborate closely between the mechanical engineering and the motion control group. And there are still areas to improve the method. For example, to find the collision points, we basically did so in almost a brute force manner, basically moving the simulation in every single point over its actuator's space, which when you use 3 axes isn't that complicated, but if you were to say to use 20 axes, this goes up exponentially over time. So for us to run that simulation took us maybe 10 to 15 minutes. If we were to run 8 axes, it might even take you a day to do so. So there are ways to improve this algorithm and make it better. So I think I am done. And if you guys have any questions, I can take that.
Well, thank you very much, Krista, for a lightning romp through. I have one question. Yeah. We saw that it stopped and wouldn't go into collision. What was the mechanism that was used to prevent it? What made it stop? Did the controller say stop?
Oh yeah, that is a good question. So basically, as you know, in the Delta Tau power brick, we have software limit switches, and these software limit switches are continuously calculated in function of the 3 encoders. So basically, we have a few PLC. I say PLC, but let's call it just embedded microcode running continuously, recalculating the software limits of each axis. So that means you can, when you run into collision, you can actually go out of it as well, because it will say you cannot go to the left, but you can go to the right if you so wish.
And so if this is as you say, a specific piece of code doing that calculation, how do you ensure that that specific piece of code is running? Does something else monitor if that piece of code is running and say, oh, it's not running, I'm not going to let anything move until it is running?
Yeah, we have a few variables that check it. So the variables are basically binary. So we have a few variables that go like, is it running? Is it if it's running equal to 0? If it's not, it's equal to 1. We don't. That's basically the end of our. How to say there. That's how far we have extended that checks. I think it can be done even further. I mean, you could check which PLC programs are currently running and stuff like this in the power brick. That could also be done in that way, actually.
Okay, thank you. Any more questions for Krista?
I have one on the chat. Yeah. Hi. How are you guys?
Yeah, doing well.
Good.
Good, thank you.
So yeah, well, my question was about we saw the styrofoam mockup as a volume representing the sample stages, but what if this is also moving? How do you do the calculations? You update this volume on the fly?
Yeah, it is a very pertinent question. The volume that you saw, I don't know if I have time to share it, but basically the volume that you saw the styrofoam doesn't actually look like the real sample stages you saw in the real picture. Like the styrofoam is a worst case scenario that you turn it around and it's the worst case scenario. Having said that, because it is completely dynamic, if we were to have the same control system monitor the encoders of the sample stage, they could actually continually monitor both stages, actually. That could be done, and it has been discussed, and it is a possible evolution of the system. We would have to presume the system would have to be encoded, or either that, or be very, very how to say it, the steps that use a stepper motors that are very reliable. We don't use steps over time. That would be horrible in our collision avoidance systems.
Nice. Do you predict any limitations on the, let's say, on the number of axes we can add on the delta tau kinematics, or
we did an estimation based on the current algorithm. If you have found the collision points, because those are two separate things. If you haven't found the collision points and you have the right amount of boundaries, we could at least scale it up at least until 8 axes without any problems. I think with some optimization, we could reach maybe 10 or 11. the implementation into the controller is fairly linear. It is the finding the collision points that is exponential. That is the real issue there. So just finding collision points with 8 axes might take you a day or a weekend, depending on how many points you're looking for. So that's the thing that needs optimization. And I think there's a lot of room of improvement on that part.
Okay. Yeah, I see.
Excellent. Thank you very much. Now, am I right in understanding we have to finish exactly on the hour because we're not allowed to extend beyond a certain time?
I think the final is 6:30 or something like that. But so
also
we have time to conclude.
Yeah. Any more questions for Krista then, if we have a little bit of time to conclude?
You can do it again, but more slowly if you want.
Okay. Well, yeah, I think all that remains then is for us to thank everybody for participating today. I know in breakout room 3, everybody took a full and active part in the discussions, and I sincerely hope that was able to be the case in some of the more populated breakout rooms. And that is what I think makes this workshop special, in that everybody can ask questions, has a chance to give their input, and feel part of our community of motion control at large radiation facilities. So I think that's it then. If we've got to say goodbye to everyone now, can I ask Eve-Marie to tell us where all these slides and information can be found at a future date?
Yeah, the slides are shared in the Indico, which is accessible in the ICALEPCS website. So all the colleagues sent me the slide updated today, so they are online now. And just yours, I think, Brian.
Yes, apart from mine, I can't get through the Soleil firewall. I don't think.
Exactly. So we will see that next week maybe. Yeah.
Yes, of course.
To deal with that. But
okay,
thank you to everybody for this nice presentation. I think it was a good opportunity to be together, even if it's not in a physical environment.
Okay, so it's nice if we can speak to each other outside of this biannual workshop, and we've those of us who use PowerBrick have been speaking to each other about maintaining the software, maintaining the files and the setup, Soleil and PSI and Sirius. So that has been a very useful collaboration, and I recommend that we all get together at some point and share our experiences other than on other than at this workshop, which I gather next year will be, or next time is due in South Africa. Is that right? So in 2 years' time, I look forward to seeing you and or your colleagues again. But I do hope that we have contact between now and then. So if you could all show your appreciation to the presenters once again, either with a digital hand clap or wave at the screen. Okay, thank you very much indeed.
Thank you very much.
Take care, everyone. Have a good weekend and enjoy the full conference next week. Thank you.
Thank you very much.
Thank you, guys.
Bye.
Nice.
Thank you.
Bye-bye.
Bye.
Thank you. Bye.
Okay. Julio, I didn't get to speak to you. Okay.
Okay.
Maybe he doesn't have a mic.
Maybe not, nor a camera. But hello anyway. I'm waving frantically, but it's hiding in the background of the filter.
Okay.
Do we think that went all right, everyone?
Sorry?
Do we think that went all right, everyone?
Yeah.
Yeah, I think it went fairly well.
Yeah, good. Thanks very much.
It's not the...
Thanks for doing the organization. I feel guilty that I came away on holiday and couldn't do any of the last minute stuff.
Okay, I think that the important thing is we could realize or achieve this workshop on, I think it was interesting, even running late, finally being in a virtual conference. I was,
it was interesting.
I hope everybody find interesting this approach.
Interesting, but I still hope it will be a real
the last one like this. Yes.
yeah. It worked surprisingly well, actually.
Okay,
it's
good.
Nice to see. It's nice to see that there is room for a full day workshop. In fact, for
yes, yes, exactly. All right. Yeah. Okay, everyone. Okay. I've got to go. I've got to rush. So, thank you very much indeed. Take care.
Have a nice vacation.
Cheers.